Section 26.2. Resistance. Let us begin by reviewing the outline of this section. We will start with the definition of current density and conductivity. Next, we will discuss Ohm's law, exploring the difference between opomic and non-opomic materials. Then, we will formally define resistance and resistivity, looking at how they depend on a conductor's physical properties. We will also cover the standard color coding used for resistors in electric circuits. Finally, we will apply these concepts to calculate the radial resistance in coaxial cables. Whenever a potential difference is maintained across a conductor, it establishes both an electric field and a current density within the material. We define current density, represented by the letter J, as the current per unit area. Mathematically, J equals the current divided by the cross-sectional area. It is also equal to the product of the charge carrier density, the charge, and the drift speed. The standard unit for current density is amperes per square meter. It is important to remember that this specific relationship is valid only when the current density is uniform and the cross-sectional area is strictly perpendicular to the direction of the current flow. In many materials, the current density is directly proportional to the applied electric field. We write this as J equals sigma times E, where sigma is the constant of proportionality known as the conductivity of the material. This leads us to Ohm's law, which states that for many materials, including most metals, the ratio of current density to the electric field is a constant value that is entirely independent of the electric field producing the current. Materials that obey this simple linear relationship are called ohmic materials. On the other hand, materials and devices that do not follow this direct proportionality are classified as non-ohmic materials. Here we see a portrait of Georg Simon Ohm, a German physicist and high school teacher who lived from 1789 to 1854. He is best known for formulating the fundamental concept of resistance. Through his extensive experiments, Ohm discovered the direct proportionalities between current density, electric field, and potential difference that we still rely on today. His pioneering work in electromagnetism laid the foundation for how we analyze and understand electrical circuits, and his contributions are immortalized in Ohm's law and the standard unit of electrical resistance. Let us define resistance more formally by considering a wire of a specific length and cross-sectional area. The potential difference across the wire equals the electric field times the length. By substituting the definitions of current density and conductivity, we find that the potential difference equals the length divided by the product of conductivity and area, all multiplied by the current. We group these geometric and material properties into a single term called resistance, denoted by R. Resistance is defined simply as the ratio of potential difference to the current. The standard unit of resistance is the ohm, defined such that 1 ohm equals 1 volt per ampere. Therefore, the current is equal to the potential difference divided by the resistance. This diagram illustrates a uniform cylindrical conductor. A potential difference is maintained across the ends of the conductor, which we label as V subscript B and V subscript A. This applied voltage sets up an internal electric field, directed from the higher potential to the lower potential. The electric field then produces a steady electrical current through the material. The cross-sectional area is uniform throughout the entire length of the conductor, which ensures that the current density remains constant everywhere inside. The current flows parallel to the electric field, carrying charge along the length of the cylinder in this specific example. We now introduce resistivity, symbolized by the Greek letter rho. Resistivity is defined as the mathematical inverse of conductivity. Its standard unit is the ohm meter. Using this new quantity, the resistance of a uniform block of material is equal to the resistivity multiplied by the length of the block, divided by its cross-sectional area. It is critical to distinguish between resistivity and resistance. Resistivity is an intrinsic property of a specific substance, whereas resistance is a property of a particular object, depending on its physical dimensions. Specifically, an object's resistance is directly proportional to its length and inversely proportional to its cross-sectional area. When building electrical circuits, we use components called resistors to control current flow. As shown in this close-up photograph of a circuit board, the resistance value of a small resistor is often indicated by a series of colored bands painted on its body. The standard color coding system works systematically. The first two color bands represent the first two significant digits of the resistance value. The third color band indicates a multiplier, essentially the power of 10 by which the two digits are multiplied. Finally, the fourth color band tells us the manufacturing tolerance or precision of the resistor. For example, a gold band indicates a tolerance of plus or minus 5%. The two graphs on this slide highlight the difference between oesomic and non-oesomic behavior by plotting current against potential difference. The graph on the left demonstrates opassopamic behavior. Here, we see a perfectly linear relationship where the straight line passes through the origin. The slope of this line is exactly equal to 1 divided by the resistance. Conversely, the graph on the right illustrates a non-alomic material, such as a semiconductor junction diode. In this case, the relationship between current and potential difference is distinctly nonlinear, meaning the resistance changes depending on the applied voltage, violating Ohm's law. Let us look at a practical example involving a coaxial cable. We want to calculate the radial leakage resistance of the polyethylene plastic insulation separating the inner and outer conductors. Because the cross-sectional area increases as we move outward radially, we cannot use the simple block resistance formulas. Instead, we must define a thin, differential cylindrical she-will of thickness, dr. The surface area of this she-will is 2 pi times the radius, r times the length, l. To find the total radial resistance, we set up an integral from the inner radius a to the outer radius b. After integrating, we find that the total resistance is remarkably high, at 1.33 times 10 to the power of 13 ohms, minimizing current leakage. To summarize this section, we established that current density is the amount of current per unit area, and it is directly related to the drift velocity of the charge carriers. We explored Ohm's law, which states that current density equals conductivity times the electric field, providing a constant relationship for ohmic materials. We learned that the resistance of an object is calculated as the potential difference divided by the current, and geometrically, it equals the material's resistivity multiplied by length divided by cross-sectional area. Resistivity itself is an inherent property of the material, varying significantly between conductors and insulators. Finally, we noted that non-ohmic devices possess a nonlinear relationship between current and voltage. To wrap up, consider these two review questions to test your understanding. First, if a cylindrical wire has both its radius and its length doubled, will its overall electrical resistance increase, decrease, or remain the exact same? Try to explain your reasoning using the mathematical relationship between resistance, length, and cross-sectional area. Think about how doubling the radius affects the area. Second, explain the fundamental physical distinction between resistance and resistivity. As a helpful analogy, how does this distinction compare to the difference between the mass of an object and the physical density of the material it is made from? Take some time to reflect on these concepts.